So we obtained that if ever my function is, if it can be written as a trigonometric series with a trigonometric series expansion, so something like this, a0 over 2 plus a sum of an cosine nx plus bn sinus of nx. Okay, so that would be 2 pi periodic function. We found that the coefficients would be given by those formulas for the an, so you just integrate your function against cosine kx and divide the result by 1 over pi, and the integration on 1 pi, that gives you coefficient ak, and some very similar stuff for the bk, where you integrate against a sinus. Okay, some very, very direct result is that if ever your function f is even, okay, if f is even, what do you get? Every time you're going to perform this integration, you've got an even function times sinus, which is an odd function, and you're integrating on a period centered in 0. So that means that the resulting function here, that would be odd, and so the integral will give you 0. Okay, so what does that mean? If f is even, you get only the cosines in the expansion, because all the bk, all the bn's would be 0. Now, very similarly, if f is odd, what's happening? You get odd times odd function. In that integral, you will get odd times even function, so that's going to give you an odd function, and so when you integrate, same stuff as before, that's going to give you 0, so you would select only the sinus terms, right? So if you have an odd function, you will get only the sine terms, okay? Next thing, what can we do when we still have a periodic function? So it's not going to work for non-periodic functions, well, unless we arbitrarily periodize them. But if your period is not 2t, well, it's just going to be a very simple substitution in your function. You can create, so let's say you've got a function of period 2 times t for some value of t. You can create an auxiliary function. Let's call that f tilde of t. Sorry, I've written too much. F tilde of t, this one, which is just a substitution of your original variable. So instead of plugging x, you'll plug t times x over pi. Okay. So this is the substitution we have. X is equal to big T times new variable t over pi, and that f tilde is going to be 2 pi periodic. So you can apply the coefficients for the f tilde. That's what you the formulas we had earlier. Okay, for the a0, an, at, and then you can just put correctly your substitution in the integral, and maybe that's a good point for you to pause and find that again. You will get these formulas for the coefficients ak and bk, and then get back again to a new formula for your original f function with period 2t. Then what are we going to do if you are given some function that is, well, let's say non-periodic? So non-periodic function defined on some interval. So it has to be a bounded interval, okay? Otherwise it's not going to work for this kind of tool. Okay, let's say that it is possible. We haven't studied yet the theorem that tells you it's going to be possible, but it is possible. So let's say you've got some function defined on some interval 0L. Okay, so it does, I don't know, something that some function might do, something like this. Let's say something like this. We want still to get some kind of trigonometric expansion. Well, a trigonometric expansion. So what we're going to do is we're going to periodize this function. And we have many ways to do that. One way would be to say, well, I'm just going to extend that by periodicity. Just saying, well, that's my original function f, and I'm just going to say, well, I'm going to define it on R by saying it's just the same period replicated as many times as needed. Okay, well, an infinite number of times. So I can and then I can consider my new function of period 2L and do the usual thing, well, the thing that we did before in order to get the coefficients. Okay, that's one way. You would get some cosines and some sines and just compute them as ever. But we have other possibilities. Okay, let me erase this one because maybe that's good. No, not the original function. Sorry. Okay, we can get better periodization of our function. What we could do is periodize it with some parity. Why? Because if so let's say this is an even extension of my function. Okay, so I've extended my function by doing an even extension between negative L and 0. Okay, so I've just replicated my function that way, and then, well, we just periodize. So what would that be? Something like this, and so on. Okay, so what's the good thing about this? This is an even function now. This is a periodic even function. So if I use this extension, I will get a cosine series. Okay, a series that a trigonometric series that contains only cosines, and so with my even expansion, I would get some. So I would get some a0 term plus some ak cosine. So we said for 2L periodic functions, it's k pi over Lx. Okay, my sum on AK. All right, but that's not the only way. Of course, I could periodize it by odd parity. So what would I get? Something like this, right? And so my function now becomes something like that. So by odd parity, I would get something like this. That would be the other one, and that would be the other one. All right. So if I consider again my 2L period, I've got an odd function. So that's odd extension of my original function. And in that case, what do I get? I will get a series with only sinuses inside, with sines. Okay, so I would get something like no more constants, because actually the constants corresponds to the 0 index, and the 0 index is going to be 0 for the sinus, and well, that gives me a cosine of 0 for the other one, and that's the one. So the constant coefficient in the trigonometric series actually goes together with the cosine. It's the cosine of 0 times pi over Lx. Okay, so if I've got now in my odd extension case, I will get only a series with some sinuses, and my function will be expanded as sum of bk sinus of k pi x over L. Okay, so from 1 to infinity. All right, with no constant terms, but that's okay, because the constant term would be the value in 0. And here we don't have one value in 0. We've got some discontinuity, but we have said nothing about the continuity requirements for the function f. Okay, we just started with the hypothesis that we could get trigonometric expansion. Okay, good. Okay, next, what about functions with complex values? Okay, so let's assume they are going to be 2 pi periodic, because of course that makes it much easier to compute. That should remind you of the first of the curves you saw in the videos in the video of Tribou, Brown that were drawn using the circles. Okay, so the small circles are actually going to be those exponentials with different frequencies, and that are going to wrap around your x, and so you're summing them, and you create something, a curve that belongs, well, you create a function with complex values. Okay, so let's say that the complex Fourier series of a function, let's give that a name, that would be S of f, the same way as we defined the trigonometric series earlier. It's going to be an infinite sum of such complex exponentials, but this time notice that my sum goes from negative infinity to plus infinity. Okay, so I must add as well as positive frequencies, negative frequencies. And you can do this exactly the same kind of computations, and that's also some of the basic integrals that you can perform. If this expansion holds, okay, what does it mean? Sorry, what does that mean? It means that if this is approximating f of x, you just integrate that against, you're performing the integration of f of x against an e minus I k x, okay, dx, and on one side you will get, well, that integral. On the other side you will get a sum of ck integral of cn, sorry, integral of e I n k times e minus I k x dx, and again this is going to give you 2 pi times delta kn. Okay, the delta being again that Kronecker symbol equal to 1 if k and n are equal to each other and 0 otherwise. Right? That's why you get in the end that formula for the kn coefficient of my complex trigonometric series. 1 over 2 pi integral between negative pi and pi of my function times e minus k x dx. Okay, and keep in mind that k is an integer from negative infinity to plus infinity. Similarly, you can perform a substitution in order to use this formula for functions that would not be 2 pi periodic but 2L periodic. Okay, for a 2L periodic function, that's the formula you will get. Okay, so don't worry for the tests in general. You will have, I will give you the formula, I will remind you the formulas, but it's good to, well, have an idea exactly what they look like when you have to divide by 2t, whereas you've got the t inside of the exponential. Okay, so that's it for the complex series. And if ever you want to use the complex expansion for a real function, that's possible, of course, and you will have the following relations between the complex Cn coefficients and the real An and Bn coefficients. Okay, of course, keep in mind that anytime I'm writing this e I k x, that means I'm considering that means cosine of kx plus I sinus of kx. Okay, so the relation between those coefficients are going to be, well, first of all, you will get that if your function is real, then the Cn coefficient is going to be related to the C minus n, so minus n corresponding to n here or minus n here. There are going to be conjugate values, so that actually if you know that your function is real, then even the complex expansion should be real, so that the imaginary part should cancel. Okay, so that's why you have this relation between those two, and then of course using that you find that the coefficients of you will get those relations for the Cn coefficients, and that's of course if you have that Cn and C minus n are conjugate, then the an that are the ones in front of the cosine are going to be given by that, and the bn would be given by this relation. Okay, good. Okay, and let us end this section with this citing the nth harmonic or the overtone of a function. It's going to be what has index n or negative n, the part with the index n or negative n in the complex expansion. Okay, next we will see the theorem that tells you that actually this Fourier series expansion exists for a lot of functions.